Okay, welcome to the lecture for Interchapter C, Stereochemistry in Nomenclature. What we are going to cover in this chapter is we are going to cover R and S naming system for stereocenters. We are also going to figure out how to name double bonds that cannot be named using cis or trans. So you can see on the outline for the lecture that those are the two topics that we're going to cover. In this first video, we're going to talk about naming asymmetric carbons using the RS system. So here's the general approach for naming asymmetric carbons. What we first want to do is identify any asymmetric carbons. Remember that asymmetric carbons have 4 different groups attached based on what we went through in Chapter 5. So if you have an asymmetric carbon, then it can be named using this system. Then we're going to go through and determine the priority of the attached groups. We're going to go through several examples, but the first thing we're going to do is looking at the atomic number. Then we're going to look at the number of groups. So atomic number, for example, a bromine would have a higher priority group than a carbon, and a carbon would have a higher priority than a hydrogen. Then we're going to look at number of groups, meaning something that is attached to 2 carbons will have a higher priority than something that's only attached to 1 carbon. The next thing you're going to be doing is putting the lowest priority group in the back. So whatever your number 4 is, often it's going to be a hydrogen, but it's not always. You'll rotate the molecule to put that group in the back. And then we're going to draw an arrow indicating the order of priority of the top 3 groups. If you go and draw your arrow clockwise, you're going to get R. So this is our clockwise arrow shown here. And if you go counterclockwise, you're going to get S. So S is shown there. And the way I always remember these is the way you start drawing an R or drawing an S. So with the letter R, we start drawing towards the right in the clockwise direction. And with S, we always start going counterclockwise. So that's how we are going to figure out and remember what we're doing for R and S. Okay, let's go through some examples. Let's start with an easy example. In this example, I'm going to start with the hydrogen, the lowest priority group already in the back. So as we draw the groups in, let's put a bromine here, how about a fluorine, and a methyl group. Okay, so first thing, let's go through and determine the priorities of the attached groups. Bromine is our highest priority group, so it's going to get a 1. Atomic number, if we go down, fluorine would get a 2, carbon would get a 3, hydrogen would get a 4. That hydrogen is the lowest priority group, so it's already in the back, so we're good. Next, we're going to draw an arrow from 1 to 2 to 3, and you'll see that when we draw that arrow, we're going to go counterclockwise. So a counterclockwise arrow would give us S, stereochemistry. Okay, here's another R and S example. In this one, we can go through and you can see that our first priority group, or our highest atomic number, is bromine. Our second priority is chlorine, and our third priority is carbon. Our fourth priority group is the hydrogen. The problem with the hydrogen, the way it's oriented, is it's sticking out at us. Okay, so we have to rotate that hydrogen so that it goes to the back. And you can see in the picture here down from your textbook, they're trying to show you how the hydrogen is rotated to the back. So the rotation that we're doing is the hydrogen to where the chlorine is, the chlorine to where the carbon is, and the carbon to where the hydrogen is. So we're holding the bromine the same, and we're just rotating those 3 atoms. If you're having a hard time seeing it, you probably want to use a model kit. If you don't have a model kit, there's a great one online that you can use. This is a virtual molecular model kit. If you want to go ahead and use it, it's awesome. Let's zoom in and take a look at our molecule. So this is the one that we were looking at in the previous picture. You can see the bromine at the top in red, the chlorine is here in green, the hydrogen in white is sticking out at us. So if we were going to do this, just as we did in the previous picture, we'd take that hydrogen and we'd rotate towards the back. Okay, so notice that the bromine's still at the top. Now the hydrogen's hiding in the back, and we've got the bromine in the same position. And so if we're going to go through our priorities, we'd go from bromine to chlorine to methyl group. So that's how we get our S priority for this molecule. Here are some more examples of how to rotate these compounds. So you'll notice in the top example here, we have a molecule that is S, and the bottom we have a molecule that is R. Depending on whatever picture you get, you should be able to rotate any of these top ones to get to that S picture. And so you need to practice and see if you can get there. So you'll notice in the first example here, to get the hydrogen to go to the back, we would have to rotate it. So you can put the hydrogen where the OH is, you can bring the OH forward and the chlorine over. And that would get you to this picture over here that looks like a Newman projection. Okay, and you can imagine if you build that model and you rotate the hydrogen to the back, this is what this would look like. In the second picture, what we have is we have the hydrogen on top. Again, we're going to have to rotate the hydrogen to the back. And so you can practice doing this. So the hydrogen would go down to where the OH is, the OH would go to the methyl group, and the methyl group would go up to the hydrogen. Notice that in this case, I'm holding the chlorine the same. And when I do that, you would also get that picture over there on the right. For the third one, where's that hydrogen now? Now it's sticking out straight in front of us. So you would rotate that hydrogen to the back where the chlorine is, rotate the chlorine over to where the OH is, and bring the OH up to the front. Okay, and that's going to get us to that picture on the right. You can see this last one, the hydrogen is already in back, so this is going to look a lot more. We just kind of have to rotate to hide that hydrogen, and we'll get to this picture on the right. The bottom ones, why don't you try on your own and make sure that you can build the model and rotate all of them and convince yourself that those are all R. Just a quick recap on how we do the priorities. Remember that our highest priority group is going to be highest atomic number. So our chlorine is going to be priority 1, oxygen is priority 2, carbon is priority 3. And so that's how we get the arrow going 1 to 2 to 3, and we're getting S. In this next example, we have a couple of groups that are the same. So if we go by atomic number, we know that chlorine is priority 1. We also know that our hydrogen is priority 4. But the other two groups that are attached are carbons, and so they have equal priority. So we have to go down the chain to see what's attached. The right carbon here has 1, 2, 3 hydrogens attached. The left carbon here has 2 hydrogens and a carbon. So because it's attached to a carbon, that has a higher atomic number than all of the hydrogens, and so the left is going to get our second priority. So this will be our priority 2 group, and the methyl group will be our priority 3. We can just ignore that priority 4 group in the back, so we're going to go 1 to 2 to 3, right? And the way we do that, we're going to get our S stereochemistry. What happens if we have a double bond? A double bond counts as 2 bonds. So if you can see down here in this bottom example, let's go through and do our priorities there. We have 3 carbons attached to that stereo center. Well, this methyl group over here isn't attached to any other carbon, so it's going to be the lowest out of those. That's going to make it priority 3. The hydrogen we know is priority 4. What's going on with the other 2? So this carbon on the left is connected to 1 carbon, and this carbon on the right is connected to 1 carbon. But the double bond counts like 2 bonds. So it's kind of like this carbon over here on the right is connected to 2 carbons. So it wins the battle in terms of priority, and it gets number 1. That means our left carbon is 2, and we go 1 to 2 to 3. and that means that we are going to have our S stereochemistry. Okay, so at this point, pause the video and do clicker questions 1 and 2. So we've been naming things R and S, and just in case I didn't already say it, the relationship between the R and the S groups are enantiomers. So if we have an R stereocenter, then we know automatically that its enantiomer is the S stereocenter. So in this example over here, let's do really fast our priorities. Chlorine would be priority 1, oxygen is priority 2, carbon is priority 3, our priority 4 group is in the back, so we're going to go 1 to 2 to 3, and that is our R stereochemistry. In the S example, they're flipped. So we're going to go 1 to 2 to 3. That's our S. So anything that has an R stereocenter is going to be an enantiomer of something that has an S stereocenter. If we go back and look at our example of thalidomide, you'll notice that the 2 enantiomers that we talked about were in fact R and S. So let's go ahead and look at how we would do priority for this bottom one. Remember, there's a hydrogen hiding here in the back. One important thing to keep in mind is that your hydrogen is going to be drawn in. In this case, it's going to have a hashed line because that's the only one that's missing. And that hashed line is going to have to go next to that wedged line. So if we draw in the hydrogen on the top, then it would be a wedged line. And make sure, it's very important to make sure that your hashed and your wedged lines are next to each other like that, or they will not be interpreted correctly. Hopefully you understand why it would be incredibly wrong to draw your hydrogen over there. Okay, if you try to build a model, it's just not going to make any sense. So when you go through, make sure that you draw your hydrogen so it is next to the nitrogen. Or in this case, the wedged line is next to the hashed line. Okay, so let's go through and do the priorities. We've got our nitrogen, priority 1, and we know that our hydrogen, priority 4. So this one's easy, it's already in the back. Next we have to compare the 2 carbons. The top carbon and the bottom carbon are both the same in atomic number, so we have to see what's attached. Top carbon is connected to a carbon on the right. Bottom carbon is connected to oxygen and a nitrogen, so that's going to be our priority 2 group. Priority 3, and now we can go 1 to 2 to 3, and what do we have that way? We have our S. Okay, you'll notice that in the top example of R, our hydrogen is sticking out at us, but because we flipped that stereocenter, we know that it's R. So please go through and convince yourself that it is R. I'll put the priorities in here. Okay, please convince yourself that when the hydrogen is sticking out at you, it is R. So one thing that we saw when we were doing stereochemistry was that we could use the terms cis and trans to describe our enantiomers and our diastereomers. However, we need a little bit more specific terminology to name some of these. For example, you'll notice that our cis molecule over here on the top left is different in stereochemistry from our cis molecule over there on the right. And so we need to be able to use our S and our designations to name all of these. A couple other interesting things that you might want to know. Remember how we said that R was an enantiomer of S? In molecules that have multiple stereocenters, you see the same sort of pattern. So SR over here on the left is the enantiomer of RS on the right. And RR on the bottom left is the enantiomer of SS on the bottom right. So hypothetically, if you were given a molecule and all you were given was the structure and being told that it was RR, you should be able to draw SS or draw the enantiomer just by flipping all of the stereocenters. Let's do the priorities just to make sure everybody understands what's going on here. Don't forget to draw on your hydrogens, and don't forget to draw on your hydrogens with the hashed lines next to the wedge lines. Okay, so in this top left example, bromine is the highest priority group. The hydrogen is in the back, so that's going to be our priority 4. We have 2 carbons, top carbon, left carbon. Top carbon is connected to another carbon. Left carbon is connected to another carbon. Okay, so let's keep going down and seeing what they're attached to. So we've got a carbon, then a carbon, then a carbon. On the left one, we have a carbon, then 2 carbons. So because that left carbon is connected to 2 carbons, it's going to beat out the top carbon in terms of priority. So this is going to be our priority 2 group, and the top one is our priority 3. So we're going to go So we're going to go 1 to 2 to 3, and that is our R stereo center. Let's do the left side now. Hydrogen's easy. It's priority 4. We have a carbon on the left, a carbon on the top, a carbon on the right. How do we differentiate these? Left carbon is 3, priority 3, because it's not attached to anything but hydrogens. The top carbon is connected to 1 carbon. The bottom carbon is connected to a carbon. Where do they differ? They differ over here. So we have carbon, 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 and on the bottom we have carbon, carbon, bromine. The bromine wins the battle, so this becomes our priority 1. Top becomes priority 2. We go 1 to 2 to 3. That makes S. Now, as you go through the rest of these, please walk through and make sure that you are able to get R and S for each of the stereo centers. Notice that it's a little bit more challenging if the groups are in the back, and you might have to do some rotations. Another way to think about this is if you go through and you draw a hydrogen in over here, that's your lowest priority group, and it's sticking out at you. If it's sticking out at you, remember that we said R was clockwise and S was counterclockwise. You can also go through and determine priorities, and if you're getting the opposite of that, so if you're getting R counterclockwise and S clockwise, if that lowest priority group is sticking at the back. So if the lowest priority group is sticking out at you and you get your groups to go clockwise, it's actually S. Rather, when the lowest priority group is in the back, clockwise means R. Hopefully that makes sense. Okay, so we got a couple more examples here. The important thing on this slide is recognizing that RSS, if we were given the name of this molecule and that was it, and you were told to draw the enantiomer, you just flip everything. So we go from RSS to SRR. And these are perfectly enantiomers. And you'll notice looking at the drawings that we've flipped every single stereo center. In the bottom example, you'll see that if we just flip 1 or 2 of those stereo centers, we don't get an enantiomer, we get a diastereomer. So this bottom right one, we flip 2 stereo centers and we have a diastereomer rather than an enantiomer. If you were to draw on the hydrogens, make sure that you're drawing in the hydrogens next to those hashed lines. Okay, it doesn't matter which side you draw them on, as long as they are next to each other like that. If they're across from each other, it's not going to work. You'll get the wrong answer every time. I should also point out that when you're doing these problems in sapling, make sure that you draw all of the hashed and the wedge lines and you draw on all the hydrogens, or it may cause problems with the grading. Here are a couple more examples. So what's interesting about this one is we're looking at some of those compounds that we said were chiral versus achiral and meso. So remember that our chiral compounds do not have a plane of symmetry, whereas compounds that are achiral and meso have a plane of symmetry. So we have over here on this right molecule a plane of symmetry, and that designates it as achiral and meso. Because we have stereo centers that we can name R and S, that means that we're going to have the possibility of being meso. And it's because of that plane of symmetry that we're meso. If we didn't have that plane of symmetry, it'd be chiral. And if we were not able to name R and S, then it would just be achiral. As we're going through and looking at these examples, you'll see a couple of things. One, you kind of notice a pattern here, that we have those two S stereocenters and we have the two R stereocenters in the bottom. So if you have an R and an S, there's a chance that you could have a compound that has some symmetry to it or could potentially be meso.